Today we will learn the second key point of semiconductor diodes in their basic circuits, the formation of a p-n junction. Next, we will study the following aspects. Formation of a p-n junction. As the name implies, a p-n junction must consist of both p-type and n-type semiconductors. As shown in the figure, when trivalent impurity elements are doped into the left side of a semiconductor, a p-type semiconductor is formed, and when pentavalent impurity elements are doped into the right side, an n-type semiconductor is formed. We know that in a p-type semiconductor, the majority charge carriers are positively charged electron holes, and the minority charge carriers are negatively charged free electrons. In addition, the p-type region contains negatively charged acceptor ions. In an n-type semiconductor, the majority charge carriers are negatively charged free electrons, and the minority charge carriers are positively charged electron holes. The n-type region also contains positively charged donor ions. It should be noted that even after doping, the entire semiconductor remains electrically neutral. There are still many silicon atoms with complete covalent bonds in the semiconductor, but they do not affect the formation of the p-n junction, so they will not be discussed here. Obviously, near the interface between the p-type and n-type regions, the concentrations of electron holes and free electrons differ greatly. This concentration difference causes them to diffuse into each other's regions. Once electron holes and electrons diffuse into the opposite region, they are easily recombined with the majority charge carriers there. After diffusion, the p-side loses electron holes, leaving behind negatively charged acceptor ions, while the n-side loses electrons, leaving behind positively charged donor ions. These immobile ions form an electric field called the internal electric field. The direction of the internal electric field is from positive ions to negative ions, that is, from the n-side to the p-side. As majority charge carriers diffuse, the internal electric field gradually strengthens. However, the direction of this field opposes the diffusion of majority charge carriers. Therefore, as the field increases, diffusion slows down. Although diffusion is suppressed, the internal field promotes the drift of minority charge carriers toward the opposite region, in a direction opposite to diffusion. When the drift of charge carriers and diffusion reach dynamic equilibrium, the internal electric field becomes relatively stable. This electric field region is the so-called p-n junction, also known as the space charge region or barrier region. Since there are few charge carriers in this region, it is also called the depletion region. In the entire semiconductor, this region has the highest resistivity. What are the characteristics of a p-n junction? First, the p-n junction has unidirectional conductivity. When an external voltage is applied to a p-n junction, if the potential of the p-side is higher than that of the n-side, the p-n junction is said to be forward biased, and the applied voltage is called forward voltage. Conversely, if the potential of the n-side is higher than that of the p-side, the p-n junction is reverse biased. When a p-n junction is forward biased, the external electric field opposes the internal electric field, weakening it. The space charge region becomes narrower, the p-n junction resistance decreases, and diffusion of majority charge carriers becomes easier. Under the forward voltage, a diffusion current formed by majority charge carriers flows in the circuit. This is called forward current. The direction of current is defined as the direction of positive charge flow. So forward current flows from the p-side into the n-side. As the applied voltage increases, the p-n junction's electric field is further weakened, and diffusion current continues to rise. Experiments show that within the normal operating range, a significant change in current will occur. indicating that under forward bias conditions the p-n junction has a very small equivalent resistance. This state is also referred to as the conduction of the p-n junction. Since the resistance of the semiconductor material itself is small compared with the p-n junction resistance, most of the applied voltage drops across the p-n junction. When a p-n junction is reverse biased, the external electric field generated by the applied voltage is in the same direction as the internal electric field, enhancing its effect. The space charge region becomes wider, the p-n junction resistance increases, and the diffusion of majority charge carriers becomes more difficult. However, this promotes the drift of minority charge carriers. At this time, a drift current formed by minority charge carriers is generated in the circuit, flowing from the N side into the P side. Since the concentration of minority charge carriers is very low and their number is extremely small, the reverse drift current is very weak, and the p-n junction can be regarded as essentially non-conductive. This state is also referred to as the cutoff of the p-n junction. Because the number of minority charge carriers is limited, increasing the reverse voltage does not significantly increase the reverse current, which tends to stabilize. This current is called reverse saturation current, denoted as IS in characteristic curves. Note that minority charge carriers are generated by intrinsic excitation, so temperature greatly affects the reverse saturation current. From the above analysis, we conclude the unidirectional conductivity of the p-n junction. 1. When forward biased, the p-n junction exhibits low resistance and a large forward diffusion current. 2. When reverse biased, the p-n junction exhibits high resistance and only a small reverse drift current. The p-n junction's characteristic curve can also be quantitatively described by its characteristic equation. Based on previous research, the current-voltage relationship of a p-n junction can be expressed as an exponential equation. In the equation, ID is the current through the p-n junction, flowing from P to N. Vd is the voltage across the junction with the same polarity as forward bias. E is the base of the natural logarithm, and Is is the reverse saturation current. For discrete devices, its typical value is less than 10 nanoamperes. For integrated circuits, the Is value is even smaller. Vt is the thermal voltage, proportional to the Boltzmann constant and absolute temperature, and inversely proportional to the electron charge. At room temperature, 300 Kelvin, Vt equals 26 millivolts. Further analysis of this equation shows if the p-n junction is forward biased and Vd is several times larger than Vt, the exponential term in parentheses is much greater than 1, and ID increases exponentially with Vd. When the p-n junction is reverse biased, Vd is negative. If its absolute value is several times larger than Vt, the exponential term approaches 0, and ID is approximately negative Is. In other words, at constant temperature, the reverse current is essentially constant and does not vary significantly with reverse voltage. This exponential equation describes only the forward and reverse bias states, not the reverse breakdown state, which we discuss next. The reverse voltage of a p-n junction cannot increase indefinitely. When the reverse voltage exceeds a certain value, the reverse current suddenly rises, indicating that the p-n junction has undergone reverse breakdown. The voltage at which breakdown occurs is called the reverse breakdown voltage. After reverse breakdown, the current is large, the temperature rises, and the p-n junction can be easily damaged. Although the causes of breakdown may differ, they all ultimately destroy the covalent bonds of silicon atoms, sharply increasing the number of free electron-hole pairs. If after breakdown the product of reverse current and reverse voltage does not exceed the p-n junction's power dissipation rating, the breakdown is reversible. This is called electrical breakdown. When the reverse voltage decreases, the p-n junction can return to its cutoff state. If the product of reverse current and reverse voltage exceeds the p-n junction's power dissipation, overheating will destroy the junction. This is thermal breakdown. Electrical breakdown can be utilized, but thermal breakdown must be avoided. The breakdown voltage depends on the manufacturing parameters of the p-n junction. Another important characteristic of the p-n junction is its capacitance effect. When forward biased, majority charge carriers produce a large forward current. In reality, during majority charge carrier diffusion, they do not all recombine within the barrier region. Many pass through the junction and accumulate near the opposite side. For example, when electron holes diffuse from the p side to the n side, immediately after crossing the junction, the probability of recombining with free electrons is low, so the concentration remains high. As the electron holes continue moving into the n side, recombination probability increases and concentration decreases. Thus, the concentration distribution of residual electron holes in the n side is as shown in curve Pn. These residual electron holes can be regarded as stored charge on the n side of the p-n junction, similar to one plate of a parallel plate capacitor holding charge. Free electrons diffusing from the n side to the p side produce a similar effect. The concentration change resembles curve Np. This equivalent capacitance of the p-n junction is called diffusion capacitance. The stored charge depends not only on doping concentration but also on the applied forward voltage. When reverse biased, changes in the applied voltage cause the space charge region width to vary, changing the amount of stored positive and negative ion charge, similar to changing the charge on the plates of a parallel plate capacitor. At this time, the capacitance effect exhibited by the p-n junction is called barrier capacitance. The equivalent value of barrier capacitance depends on the applied reverse voltage. The capacitance effect of a p-n junction directly affects the high frequency and switching characteristics of semiconductor devices. A p-n junction, like life itself, involves give and take. Nothing can be gained without some loss. Everything is a process of balance. Do not force it and do not seek gain without accepting loss. That concludes today's lesson. Thank you for listening.